Hey everyone, I got a new shipment of PCBs the other day, so I figured this is a good opportunity to show how I put one of these together and talk a little bit about what the different stuff on this board is for. So these boards are pretty similar to the one in here, but with a few improvements. The biggest of which is that these are 4-layer boards, while the previous one here was a 2-layer board. My reason for making the switch was that the 2-layer version suffered from a lot of noise issues. I think I did a really bad job laying out and organizing the signal return paths on this board, so a lot of noise from the digital signals, especially SPI, is making its way into the analog audio section. My hope with these new boards is that by having solid, uninterrupted ground planes, I can have direct return paths under all the signals and avoid any noisy loops and such. I have no idea how well this is going to work, but we'll be able to find out after throwing a few components on here. The other changes are more minor. We have on the new PCB 2 additional 3.5mm jacks, one for line level output, and one all the way over here on the end for an external FM antenna. I also added an option here for using a larger capacity serial flash chip. Now I ordered these like a month ago, and since then I've gotten a number of suggestions in the comments of other videos about improvements I can make to the hardware and the layout. First was this comment here from Sunwoo, who just suggested expanding the keyboard a little to make sequencing more efficient. I definitely agree that this would be an awesome addition, but it will require some reorganizing of the button layout here. I could maybe try squishing the white keys on the keyboard and tuck 2 more keys in there. I could even throw in some RGB LEDs for indication. I don't really know yet, the layout always takes a while to figure out, and this is a work in progress. The other tip came from Simon Merritt here, who's mentioned that the PCB could maybe be put into one of these 60% keyboard cases. This one really blew my mind because I didn't know these things existed, and they just happen to be almost exactly the same dimensions as my current board. And on top of looking way better, it'll definitely be more durable than my 3D printed case here. They are a little pricey though, so I'll probably just have to put in an option for it to be swapped out for a 3D printed version. Lastly, this dude, whose name I'll most certainly butcher if I try to pronounce it, suggested using RGB illuminated encoders. I think that'll look pretty sick, especially if I can print some kind of translucent knobs for them. Unfortunately, like I said, I did order these boards a while ago, so none of these cool changes I just mentioned are implemented in what we're actually building today. Also, these 4-layer boards are a little more expensive to get manufactured. Even if this does work perfectly, I'll have to look into fixing the problem and building all of the improvements back onto the 2-layer board, which JLC PCB can make for as little as like $1 each. Anyway, let's put aside this old version and get started on the PCBs. Now, as per the minimum order quantity, JLC PCB has sent me 5 copies of this PCB. We'll only be needing 1 today. Before we do anything, I realized once I received them that Gatoron has actually changed the dimensions of their switches since the last time I built this. Specifically, the new switches here have a 5mm diameter stem, whereas the old version of the switch, which this PCB was designed for, has a 3mm stem. That means all of the 47 stem holes in this PCB are too small for the switches to actually fit through. Now I really hate to have to do this, but since I wasn't about to order a new batch of boards just for this, I went ahead and drilled them out to size. I did this off camera to spare you guys all the mutilation and horror, and I'll just show you what it looks like in the end. If you have a weak stomach, I'd suggest you look away for this part. Okay, so it's not really that bad. I was able to get away with this just because the hole clearance I had used when designing this board was just barely big enough to allow me to enlarge them to the right size without interfering with any of the traces. Though admittedly, I was cutting it a little close for comfort. I did already correct the hole sizes in the PCB files on GitHub, so hopefully no one else will have to suffer through what I did. With that out of the way, the rest of this should be pretty smooth sailing. Let's get to soldering. Alright, I have the PCB in front of me and I've put it on this old silicon mat just to avoid accidentally burning my workspace with my soldering iron. Speaking of which, I'm using my little TS80 soldering iron with a regular cone tip. It's not the most ideal tool for the job. If you wanted fast and easy, you could use a heat gun and solder paste for all the SMD components on this board. But let's be honest, where's the fun in fast and easy? If you're anything like me, hand soldering all these bits is most of the fun of building something like this. I'm going to start off by putting together this lower left hand corner of the board. This is the power supply section, which steps up the voltage from our battery to the 5 volts we need to power everything on the board. By soldering this together first, we can ensure that all the correct voltages are showing up where they need to be, and there's no risk of accidentally frying anything if it turns out that any of the power supply parts aren't working. Now I have the bill of materials opened on my computer, and soldering the components is just a matter of finding the component designator on the board, R21, C18, whatever it may be, and matching that value to the one on the parts list. The parts list will then show me what particular component goes in that spot. I ordered all these parts from DigiKey, by the way. I'm going to start off with the ICs because those are usually the most challenging to solder, so I'm just grabbing those bags and setting them aside here. This one's the battery charger IC, and it can be a bit of a challenge to solder. Not only is it super tiny, but it's in a DFN package, which means its leads are only on the bottom and aren't even exposed from the top. So how does one solder this with a regular soldering iron? What I do is first cover the pad that the chip will go on in flux. I'm using paste flux that comes in a little jar, and I'm spreading it on with a little toothpick. Then we can go ahead and carefully line the chip on the pad. The nice thing about paste flux is that it's pretty sticky, and once you've positioned the IC, the flux will hold it there until you're ready to solder. Now I can take my soldering iron and apply some solder to the pad on the side of the chip, not the chip itself. Because we added all that flux, the solder will flow along the pad and wick underneath the chip, bonding it in place. This can be repeated all around the chip, and any excess solder can be cleaned up with some solder wick. For the exposed pad in the center of the chip, which also serves as its heatsink, I've put a hole in the PCB so that solder can be flowed in from the other side. So I actually filmed the entire soldering process for the whole board, but looking back at it, I don't know how useful any of the footage is, especially since I don't have one of those microscope cameras to show you what's happening up close. So I'll just fast forward through most of it and jump in when anything important happens. Okay, so you just saw me finish up the power supply section. I've gone ahead and soldered up a single cell LiPo battery to the connection point down here, and with the device switched on, as you can tell by the red power indicator LED being on, I'm going around the board with the multimeter and checking that I'm getting a solid 5 volts in the place where it's needed. I'm finding the spots to check using my board layout, but I'm probably going to add in some labeled test points right into the PCB in the finalized design to make this a little bit easier. Everything is looking good, so now I can disconnect the battery for safety and continue with soldering the rest of the board. There's no particular order I use for putting the rest of the board together. I did, however, make sure to get all of the SMD components soldered on both sides of the board before moving on to the bigger components like the switches or encoders. This is just so that I could lay the board flat while soldering the small, finicky parts. Now, I'm no soldering expert, but in my experience, there are a few things you can do to make this process a little bit easier. One thing I can't stress enough is how important flux is. Using extra flux will make your life so much easier, and it'll make all of your solder joints look nice and pretty. I'm a pretty firm believer that you can never apply too much flux. It may leave a residue all over the board, but this can easily be cleaned up with some acetone and a toothbrush, as you'll see me do several times in the video. Also, when soldering things like ICs that have a lot of pins that are close together, don't bother spending time trying to solder all the pins individually. Apply your flux like normal and just glob a bunch of solder on the pins, not worrying about bridging or connecting all the pins together. Once the pins have solder on them, you can go back in later with a bit of solder wick and just bump it into the pins. This will suck up all the excess solder and should leave you with absolutely perfect solder joints. Now I'm soldering all the switches, only after making sure that the keyboard diodes are all soldered in, and that they're all facing the right direction. It'll be a lot harder to go back and fix them once the switches are installed. The joystick is one of the parts that's a little more tricky to put in. Its pads are on the bottom and not really accessible in the current state. What we can do is carefully disassemble the joystick to expose its PCB, where we can directly access its solderable terminals. Now we just add a bit of solder to both the pads on the main board as well as the pads on the joystick PCB, align the joystick PCB with the outline, add a good bit of flux, and use the soldering iron to reflow all of the solder until the joints are formed. After that, a bit of solder wick is used to suck up the excess solder from the top of the joystick PCB, and a little bit of acetone helps get rid of all the flux residue. The potentiometer requires a little bit of modification before mounting it on the board. I'm just using a pair of close cutters to clip off any excess bits of metal underneath so that the bottom of the potentiometer sits upright against the board. This is optional, but it ensures that all the knobs on the board are at the same height. The encoder, on the other hand, requires no modification, and they can be slotted right into the board. Next up is the Teensy, and before I put it onto the main PCB, I'm making sure to install the two PS RAM chips on its underside. I've forgotten these before, and trust me, it's not worth the headache trying to desolder the Teensy just to get these in. I'm also soldering in the new SD card holder now while the pins are still easily accessible. This just sits right on top of the existing SD card reader, and I'm carefully bending its pins 90 degrees so that it makes contact with the pads on the Teensy. Once those are soldered in, I'm also soldering in a spare header pin to mechanically anchor the back of the SD card reader to the Teensy. And last in are the display and radio modules. For the radio breakout, I'm soldering a shielded cable from the antenna pin all the way to the 3.5mm jack on my right side, and connecting it to the pin closest to the open end. I'm just using a piece of an old audio cable to do this. And that's it. You might have already noticed that although it takes a while to put together, there's not really too much going on this PCB. Let's go in for a close-up and talk about what the various sections of the board do, starting with the power supply. As the name suggests, this section deals with supplying power to the board and can be thought of as having four main parts. The first part is the power source, which in my case is a 1S LiPo battery. This gets soldered into the board at this point here. The second part is this little circuit, which is responsible for taking power from this micro USB port here and correctly charging the battery. When a USB cable is plugged in and the battery is being topped up, we'll see this yellow indicator LED light up. Now, the LiPo battery has a max voltage of around 4.2 volts and a nominal voltage of around 3.7 volts. This isn't super useful since we need 5 volts to power the Teensy and a number of other things on the board. This brings us to part 3, the boost converter. This circuit is a little switch mode power supply, which boosts the relatively low voltage coming from the battery to the 5 volts we need at a maximum of 1 amp or so. The last part is made up of these three components here. This little guy, U4, is a battery voltage monitor. When the battery voltage gets too low, it sends a signal that disables this boost converter, thus turning off the device. This keeps the battery safe by preventing over discharge. All of this is only necessary because I'm planning to use this device directly from a battery. If you wanted to power your device off a USB power bank, for example, you could omit everything in this section because the charging, boosting, and over discharge protection will all be built into the power bank. Moving up a few millimeters, we have the audio codec and a serial flash memory chip. This is the SGTL 5000 and it deals with converting the digital audio information from the Teensy into analog audio, as well as converting external audio signals into a digital format the Teensy can understand. The circuit I used for this is pretty much taken straight from the Teensy audio shield, with a couple of small exceptions. First is that instead of powering it off the Teensy's 3.3 volt output, I have it being powered off of its own ultra low noise linear regulator. The hope with this was to better attenuate any switching noise from the power supply from reaching the codec and ruining the audio. The second change I made is adding a spot for a larger capacity serial flash IC. This is a 512 megabit or 64 megabyte module, which should give us plenty of space for audio. This guy, all the way at the top, is the LM314, which just controls the LED volume display. Putting some solder on this jumper, like I've already done, allows you to select between a bar graph style display over a dot style display. This one's just a matter of preference. This is the SI4703 breakout from SparkFun, and aside from being a nice accent piece for the back of the board, it's what gives us access to FM radio. Its audio outputs go straight into the codec's line input. My extension wire is soldered to the antenna pin on the breakout, and the shielding is just connected to the ground pad down below. That wire leads to this 3.5mm jack here, where we can plug in one of these cheap external antennas or just a pair of earbuds in a pinch. Last but certainly not least, this handsome little IC is an Atmega 4809, which some of you might recognize as the same chip on the new Arduino Nano boards. I call this the input processor, and it's the chip responsible for checking the state of all the buttons and encoders on the device and reporting them to the Teensy. I'm doing this because the Teensy 4.1 has a finite number of pins I can use, and I don't want to waste a bunch of them just to monitor the buttons. So, we can offload this task to a different and much cheaper microcontroller, and just have it tell the Teensy what's going on over I2C. That way, I only need 2 pins from the Teensy. For this guy to be able to do any of this, we need to first write some firmware for it. Fortunately, we can do this pretty easily with the Arduino IDE and program the device through these pads here. One additional thing we need in this step is a spare Arduino. This will act as a programmer for the Atmega 4809 and will serve as the bridge between my computer and the chip. I'm using an Arduino Nano I had lying around, but most Arduino boards will work just fine. On my computer, I'm going to find and download the JTAG to UPDI code from GitHub. This wonderful piece of firmware is what converts our spare Arduino into a UPDI programmer, which is the one-wire programming protocol used by the Atmega 4809 chip. Once that's downloaded, I can open it up in my Arduino IDE and upload the contents to my Nano. After that completes successfully, I'm disconnecting my Arduino from USB. Now we have to connect the programmer to the device we want to program, and to do that, I've soldered 2 wires to my programmer. The black wire connects to the Arduino's ground pin, while the white one is connected to digital pin 6. On the other end, I'm soldering the white wire to the pad labeled UPDI and the black wire to the pad labeled ground. And even though we're using the Atmega 4809 on 3.3 volts, I can safely program it from my 5V Arduino without using a level shifter, because the UPDI pin is in fact tolerant of high voltage programming. Now it's safe to plug the programmer back into my computer. I'm also plugging in a USB cable into the Teensy on the other side. All this does is provide power to the Atmega chip so we can communicate with it. If things have been soldered correctly, we should see 2 red LEDs light up on the back of the board, one on the left side of the board near the power switch and one next to our microcontroller IC. On my computer, I've already gone ahead and installed MegaCore X via the board manager, according to the instructions on the GitHub page. Now to check if everything's connected up properly, we can open up the Blink example sketch in our Arduino IDE, and make sure to change the LED pin from 13 to 7. Then, in the Tools menu, I'm selecting Atmega 4809, leaving the rest of the options at their default values, and making sure to select the JTAG to UPDI as my programmer. If everything is working well, once I hit upload, I'll be able to see a successful write output at the bottom of my screen, and on the board, I'll see the yellow LED blinking. If this is not happening, or there's an upload error, you'll have to do some debugging, including making sure you've powered up the board and ensuring all of your solder connections are good. Since my Blink test was successful, I can finally go ahead and upload the input processor code. I can see that the upload went smoothly, so now I can disconnect both boards from power and then disconnect the programming wires. This whole process only needs to be done once, and the input processor code is now stored on the Atmega 4809, ready to start up when the board is powered. As a final test, I've put in an SD card with some audio samples on it, and hooked up a 3.5mm audio cable to the line out port of the board, which connects on the other end to my audio interface. I should note that this port only supplies a line level output and is not intended to drive headphones. If I do want to use headphones, I would connect them to this port on the side, which is powered by the Codec's built-in headphone amp. Since I'm still waiting on a new battery, for the time being I'm powering up the board by plugging in a USB cable into the Teensy, and after it boots, you can see I've uploaded the code from my last video to the Teensy. Now I can go through and check some functions, like whether all the keyboard buttons are functioning properly, whether both axes of the joystick are responding, and that the samples on the SD card are accessible. So it's been a few days since that last scene, and my batteries have finally arrived. I picked up 2 of these little 2800 mAh LiPo cells from Amazon, and I'm just going to connect them in parallel to make my battery. I'll leave a link for these in the description, but our power supply circuit will work with any single cell LiPo, so feel free to substitute these with whatever you have access to. Obviously, the bigger capacity you have, in terms of milliamp hours, the longer the battery will power the device for. I couldn't find one big single LiPo, so by connecting these two smaller LiPos in parallel, I'm effectively turning these into a single battery with double the capacity and the same voltage. Now before I connect these two batteries together, there is just a little bit of preparation I gotta do. So when these batteries are shipped, they're usually charged to some storage voltage, which is around 3.85 volts. But naturally, there's no guarantee that the cells you're going to get will be at this exact same voltage. These certainly weren't. If the voltages on the batteries are too different when we connect them in parallel, both batteries will try their hardest to equalize, and that usually means a lot of current trying to go from the battery with the higher voltage to the battery with the lower voltage. Even if the batteries have protection circuits, like these do, this is not really a situation we want to risk finding ourselves in. So what I've already done with these is connected them to the board, independently of course, plugged in a USB cable, and let them charge. This way, once they were done, I could be sure that they were at the same voltage level. Just to be sure, I'll check them one more time with my multimeter. That's close enough for me, so now I can go ahead and start putting my battery together. I'm starting off by adding just a little bit of hot glue between the cells to hold them together. And then securing them with a little bit of tape. Finally, I can go ahead and solder the batteries in parallel, red to red and black to black, while being super careful not to short out any of the wires by accident. I'm just kidding, but seriously, only cut one wire at a time. With that done, I can just solder it into the battery terminals. While I was doing that, my 3D printer was busy cooking up these body pieces. These are the three sections that make up the housing, and they're just attached to the PCB with M3 bolts. I'm starting with the leftmost piece where the battery goes, and I'm dropping in some hex nuts into these recesses in the back, because the bolts need something to screw into. I also printed out all the keycaps for this thing. Now these Gatoron switches I think have a standard cherry connector on them, so you can technically just use those mechanical keyboard keycaps, but I didn't really want to spend any more money than I had to. Plus, by 3D printing them, I have a lot more flexibility with their shapes and sizes. These are obviously ready to go, fresh off the print bed, but I ended up doing a little bit of optional post-processing. First, I used a little bit of matte black acrylic paint to color all the sharp and flat keys. And getting paint all over the table in your hands like a toddler is actually a really important step in the process. That's a little industry secret for y'all. Second, since these parts are white, they're pretty prone to getting dirty, especially with my grubby fingers touching the keys and knobs all day. So after giving them a quick rinse with some soap and water, I arranged them all inside a cardboard box and hit them with a few thin layers of clear coat. This makes the surface way less porous and much easier to clean. Once those are dry, I'll just pop everything in place and add in the little cosmetic covers for the encoders and the OLED. Okay, the last thing I want to do is come back to the reason I made this new board in the first place. Remember in the beginning of this video when I said the old 2-layer board was suffering from a lot of noise? Let me show you what I was talking about. I have the old board in front of me, and with it turned on, I'm going to probe the microphone connector, since that's one place where electrical noise can be pretty detrimental to performance. You see these bursts of noise that are occurring periodically at a rate which is suspiciously similar to the rate at which I'm updating my display? Well, these are the result of the SPI signal sent from the Teensy to the OLED display getting coupled into ground, and it can be observed all over the board. I shouldn't have to tell you that a massive amount of noise feeding into our audio circuit is a pretty bad thing. For example, in the trace you're seeing right now, the noise level is almost 100 millivolts peak to peak, which is big enough to almost completely drown out any signal this little electret condenser microphone can produce. Moreover, since the noise is turning on and off with a period of 10 milliseconds or so, it actually creates an audible buzz in the signal. This is what an actual microphone recording made on this old board sounds like.
Uh-oh, so noisy.
So, not great. Let's check the same spot on the new board we just finished putting together. And there we have it, a pretty massive improvement. We can see on the scope that we have a clean signal with essentially no trace of that digital noise left, and whatever tiny bit of noise that may be remaining is too high frequency to show up in my audio anyway. Knowing that, I can finally solder the microphone into the board and complete the build. With the noise-free machine, I'll finally get a chance to explore what I can do with the audio input capabilities of this board, but I think I'll save that for the next update. I hope you guys were able to get something useful out of this video, even if you aren't planning on building this exact same thing. I know I kind of rushed through a lot of stuff, so if anyone wants more information, feel free to let me know in the comments, and I'll be happy to answer there or make an addendum to this video. As usual, you'll be able to find all the files you need and the link to all the parts I used down in the description. Thanks so much for watching, and I'll see you in the next one.